Hi, this is Yuan Bo, a PhD student at Georgia Tech. I'm presenting a work, Fast Graph Simplification for Interleaved Dyck Reachability. This is joint work with my advisor Qiren Zhang from Georgia Tech and Professor Thomas Rebs from University of Wisconsin Medicine. We motivate our work from the static taint analysis example. Static taint analysis compute which variables can be affected by predefined taint sources without actually running the program. These taint sources can be user-sensitive data, such as password. So the analysis can help developers to check whether there is potential information leakage. Considering the Java-like program, suppose that the variable VA contains user-sensitive data. We want to perform a static taint analysis to know whether it is possible for the sensitive data of variable VA to flow to variable VC. A popular approach to solve this problem is to formulate analysis as a formal language reachability problem in graphs. In the graphs, nodes represent the variables in the program, and the edges are data flows between variables. The question of whether the sensitive data can flow from variable VA to VC now becomes the question whether there is a path from node VA to node VC such that the edge labels of the path form a word in the formal language. The most commonly used language for formal language reachability problem is Dyck language. A Dyck word is a string of balanced parentheses. It is often used to describe matching conditions in the flow, such as method calls and returns, locks and analogs, pointer reference and dereferences. In our taint analysis example, we want the language to capture some matching conditions. The first one is context sensitivity. That is, in a program, after a function call, a value flow should return to its corresponding call sets. In a corresponding graph reachability problem, we need a Dyck language to model the context sensitivity. The open parentheses represent method calls, and closed parentheses represent method returns. For example, in this valid path, the open 8 parentheses represent the call at line 8. It is matched with the closed 8 parentheses, meaning that the flow returns to the call set at line 8. Similarly, to make the analysis field sensitive, in the flow, the field assignment should be matched with the corresponding field accesses rather than accesses of other field. In the graph reachability problem, we need another Dyck language to capture field sensitivity. The open brackets represent field assignments, and closed brackets represent field accesses. In this valid path, the open F brackets represent an assignment to the field F, and it is always matched with the closed F brackets representing an access of field F. When we want to track these two matching conditions simultaneously, the problem becomes an interleaved Dyck reachability problem. We call it InterDyck reachability. In the InterDyck language, a word is interleaving of multiple Dyck words. For example, this word is an InterDyck word because it is interleaved by these two Dyck words. Thus, the taint analysis is formulated as an InterDyck reachability problem. If there is an InterDyck path from the node VA to VC, it indicates that the value of variable VA in the program might flow to variable VC. InterDyck reachability is a very useful formulation and can be applied to many other static analysis applications, such as type state analysis, alias analysis, and side effect analysis. However, InterDyck reachability problem is undecidable. In practice, one can only use an approximation algorithm to provide a safe solution. The traditional approach for InterDyck reachability is to use a context-free language to over-approximate the InterDyck language and compute its reachability on graphs. The context-free language reachability algorithms almost have cubic time complexity, and it does not scale well in practice. To make InterDyck reachability scalable, many previous efforts focus on proposing better approximation algorithms. In this work, we attack the problem in an orthogonal direction. Instead of working on a new algorithm, we focus on simplifying the input graphs. The graph simplification can help InterDyck algorithms to achieve better performance because the algorithm can work on a smaller graph. Besides performance, the simplification can also help increase the precision because some false positive pairs reported by the approximation algorithm in the original graph can be removed in the simplified graphs. So how can we simplify the input graphs without affecting the InterDyck reachability result? What can we remove safely? The key insight is that if an edge is not involved in any InterDyck path, we can remove this edge without changing the InterDyck reachability result. We call this kind of removable edges as non-contributing edges. If an edge is in at least one InterDyck path, we call it contributing edge. In the following example, the closed line parenthesis edge has no matching open line parenthesis edge in the graph, so there is no InterDyck path that contains the closed line parenthesis edge. It is a non-contributing edge. Then to simplify the input graph, we only need to remove the non-contributing edges. However, we cannot compute non-contributing edges directly for InterDyck reachability because the problem of InterDyck reachability can actually be reduced to its contributing edge computation. So contributing edge computation is also undecidable for InterDyck. One can only use an approximation algorithm to provide a subset of non-contributing edges. How can we compute non-contributing edges and compute it really fast? For example, we cannot afford running any InterDyck algorithm because we know it does not scale well for large graphs. The key observation is if an edge, for example, the open A parenthesis edge, is involved in an InterDyck path, then we regard the labels of other Dyck language as epsilon. Then this edge is involved in a new Dyck path. For each Dyck language Lx in the InterDyck language, can we construct a new Lx graph such that it has the following property? For an InterDyck contributing edge in the original graph, its corresponding edge in the Lx graph is Dyck contributing. Then once we compute all the Dyck contributing edges in each Lx graph, the corresponding edge set in the original graph will be a superset of all the InterDyck contributing edges. To construct such an Lx graph, after we regard non-Lx edges labels as epsilon, we contract epsilon edges, the resulting graph will be an Lx graph. From the previous slides, we can see that an InterDyck contributing edge in the original graph is a Dyck contributing edge in the Lx graph. Then how to determine Dyck contributing? Naive way is to run the context-free language reachability. We call that the context-free reachability has about the cubic time complexity, so it is as expensive as running InterDyck algorithm in the first place and thus defeating our goal to make it scalable. To overcome this problem, we make the Lx graph bidirected. That is, for each edge in the Lx graph, we create a reverse edge with the opposite edge label. For example, here is the bidirected version of the previous Lx graph. In the bidirected Lx graph, we can adopt a much faster algorithm called Fast-Dyck algorithm, which runs in linear logarithmic time for Dyck reachability. And at the same time, we still have our desired contributing edge property. That is, any contributing edge in the Lx graph is still a contributing edge in the bidirected Lx graph. Finally, we show how to compute contributing edge using Dyck reachability. Because the graph is bidirected, for convenience, we only present the open parenthesis edges. In a bidirected graph, Dyck reachability becomes symmetric, meaning that if a node A is Dyck reachable to B, node B is also Dyck reachable to A. Because Dyck reachability is also transitive, Fast-Dyck algorithm can perform node merges when it finds two identical open parenthesis edges pointing to the same node. After all the node merges, variables in the same node are Dyck reachable to each other. Here is a node merge example. The two open A parentheses point to the same node, and the node on the left and the node on the right are merged together. To collect contributing edge information, we can see that for every node merge, the two identical edges that cause the merge are actually contributing edges, and they form a Dyck class themselves. By collecting these edges, we got a complete set of contributing edges for the bidirected Lx graphs. After running Dyck reachability for each Dyck language, the corresponding edges are the potentially contributing edges in the original graph. In the example, after computing Dyck contributing edges for two Lx graphs, we know the following four edges may be contributing edges in the original graph. The rest of the edges are definitely non-contributing edges. The final step in the simplification is to remove these non-contributing edges. We have described the major steps for graph simplification, and let me summarize graph simplification algorithm. Given the original input graph, for each Dyck language Lx in the InterDyck, create an Lx graph. Any InterDyck reachable pairs in the original graph are also Dyck reachable pairs in the Lx graph, if they still exist. Then we make the Lx graph bidirected. Dyck reachable pairs in the Lx graph are still Dyck reachable pairs in the bidirected version. We compute all the Dyck contributed edges for all bidirected Lx graphs. The rest of the edges are non-Dyck contributing edges. Their corresponding edges in the Lx graph are non-Dyck contributing as well. For every non-Dyck contributing edge in the Lx graph, its corresponding edges in the original graph are guaranteed to be non-InterDyck contributing. Then we get a subset of non-contributing edges. Finally, to get the simplified graph, the graph simplification algorithm removes this subset of non-contributing edges. To evaluate the graph simplification algorithm, we perform a context-sensitive, field-sensitive Taint analysis over 95 real-world Android applications. We also evaluate the benefits of the simplified graphs provided to three different InterDyck reachability algorithms. The first one is the traditional context-free language reachability approximation algorithm. The second one is the synchronized push-down system algorithm, or called SPDS. The last one is linear conjunctive language reachability algorithm, called LCL algorithm. In the evaluation, we first explored the effectiveness of our graph simplification algorithm, with the focus on performance and the reduction ratio with respect to the increase of the input graph size. Then we explored the benefits that the simplification can provide to this InterDyck algorithm with the emphasis on performance and precision memory usage. We first present whether the graph simplification algorithm scales for large graphs. In this figure, the x-axis is the sizes of the graphs with respect to the edge number. The graph size ranges from within 100 edges to more than 100,000 edges. The y-axis is the simplification time in seconds. We observe a linear time performance for the simplification. The result actually indicates that the graph simplification algorithm scales well for large graphs. We then present the size reduction result. In the figure, the x-axis is still the size of the graphs, and the y-axis is the reduction ratio, which is the size of the simplified graph divided by that of the original graph. We see about a quarter of edges get removed on average, and the simplification can consistently remove more than about 20% edges in most of the cases. As for its benefits for InterDyck algorithms, we perform the InterDyck algorithms on each graph with a 300-second time budget. The performance result is presented in the figure on the right. The x-axis is the size of the graph. The y-axis is the performance ratio, which is the time InterDyck algorithms running on the simplified graphs divided by that on the original graphs. The dots are speedups for LCL InterDyck algorithms. The triangles are speedups for SPDS algorithms, and the crosses are speedups for CFL algorithms. The figure shows the distribution of the speedups. As we can see, the graph simplification are likely to help InterDyck algorithms to speed up in large graphs, which indicates that the simplification algorithm can increase the scalability of InterDyck reachability algorithms. The table also shows the timeout statistics. You can see that for 13 graphs, the LCL algorithms cannot run on the original graphs but can finish on the simplified graphs. There are 5 such graphs for SPDS algorithms and 2 for CFL algorithms. Overall, the graph simplification provides about 2.18 times speedups on average for 3 InterDyck algorithms. For the precision figure, the x-axis is still the graph size, the y-axis is the precision ratio, which is the number of pairs InterDyck algorithms reported on the simplified graphs divided by that on the original graph. The smaller the value, the more the simplification algorithm help upon increasing the precision for InterDyck algorithms. On average, after simplification, InterDyck algorithm gives about 35% smaller solution set. The removed pairs are all false positives generated by InterDyck algorithms, so the graph simplification can improve the precision of InterDyck algorithms significantly. The last figure shows the benefit simplification provides to the memory usage of InterDyck algorithms. The y-axis is the memory usage on simplified graph for InterDyck algorithm divided by that on the original graphs. On average, InterDyck algorithm saves about 43% less memory when using on simplified graphs. To sum up, in our work, we provide a new perspective to improve the InterDyck reachability. Instead of proposing different approximation algorithms, we can also simplify the input graphs. We also design a new graph simplification algorithm which can identify a safe subset of non-contributing edges. We also evaluate this simplification algorithm in practice. It shows that it can provide significant performance and precision improvement for InterDyck algorithms. Thanks for coming to the talk, and I'm happy to take questions.